You throw a ball. It goes through the left doorway or the right doorway, hits the back wall, leaves a mark. You throw another, same thing. After 1,000 throws, you look at the pattern. What do you see? 2 clusters of marks, one behind each doorway. Makes sense, right? Each ball went through one door or the other, simple. Now forget tennis balls. Let's do this experiment with electrons, tiny, tiny particles, the smallest bits of matter we deal with in everyday physics. We shoot electrons at a barrier with 2 slits, very thin slits, and we have a detector behind that clicks every time an electron arrives. Click, click, click. Each click is the same, never half a click. So electrons arrive as whole things, individual lumps, particles. Good. Electrons are particles, just like tennis balls. But now we count where they land. We build up a picture of the pattern. And it's not 2 clusters, it's stripes. A zebra pattern. Lots of electrons here, almost none there. Lots here, none there. Alternating bands. This is what waves do. When 2 waves meet, sometimes they reinforce each other. Bigger wave. Sometimes they cancel each other. Nothing. It's called interference. Like when 2 ripples in a pond cross each other and create a complex pattern. So electrons are waves? But they arrive as clicks, individual lumps. We never detect a piece of an electron. It's always whole. Here's the situation. Electrons arrive like particles, but they arrange themselves like waves. Okay, maybe they're bumping into each other somehow, interfering with each other on the way. So let's slow everything down. We send 1 electron at a time. Shoot one, wait for it to arrive, then shoot the next. They never meet. We do this, very patient, one by one. Same pattern, stripes, interference. Each electron is interfering with itself. What does that even mean? Well, maybe the electron splits in half, goes through both slits and meets itself on the other side. Let's check. We put a little detector at the slits to see which way each electron goes, and we watch. Every single electron goes through one slit or the other, never both. We catch it in the act, left slit or right slit. It's a definite particle taking a definite path. But now we look at the pattern on the back wall. The stripes are gone, just 2 clusters, like tennis balls. Exactly what you'd expect from particles that go through one doorway or the other. So when we don't look at which slit the electron goes through, we get interference. When we do look, the interference disappears. Let me say that again because it sounds insane. The act of finding out which path the electron took changes the outcome of the experiment. Now you might think, well, our detector probably bumped the electron, disturbed it somehow. Physics involves interactions, right? So let's be gentler. Let's use the softest possible way to detect the electron. We try this, and here's what Heisenberg discovered. There is no gentle enough way. If your detection method can actually tell you which slit the electron went through, it will always disturb things enough to destroy the interference. And if your method is too gentle to disturb anything, it's also too gentle to give you the information. You cannot have both. You cannot know the path and keep the pattern. Nature doesn't allow it. This isn't about our technology being bad. It's not that we need better instruments. This is fundamental, built into the fabric of reality. The electron doesn't have a definite path until you look. And when you look, you force it to choose. But wait, that's strange. Before we looked, where was the electron? Did it go through both slits? Did it go through neither? Did it take every possible path at once? Here's the answer, and you're not going to like it. We don't know. And more importantly, the question might not even make sense. See, we grew up in a world of tennis balls and doorways. Things have positions. They take paths. They're somewhere. That's intuition. That's common sense. But common sense comes from everyday experience. And everyday experience is made of big things, billions and billions of atoms stuck together. At that scale, quantum weirdness averages out. You don't see it. But down at the level of single electrons, single photons, the rules are different. Our intuition doesn't apply. The words we use, like path and position and where is it, Those words might not even mean anything down there. So when someone asks, but which slit did the electron really go through? The only honest answer is, if you don't measure it, the question has no answer. Not, we don't know the answer. The question itself doesn't apply. That's quantum mechanics. That's what nature is actually like. And if you don't like it, well, nature doesn't care. Every way an event can happen, we draw an arrow for it. The arrow has a length, and it points in some direction. And here's the rule. To get the probability of something happening, you take the final arrow and square its length. So an arrow of length 0.4 means a probability of 0.16, 16%. Simple. But here's where it gets interesting. When something can happen in more than one way, like an electron going through the left slit or the right slit, we don't add the probabilities, we add the arrows first. And arrows are sneaky things. See, if you have two arrows pointing the same direction, you put them head to tail and get a longer arrow. Big probability. But if they point in opposite directions, they cancel out. Small probability, maybe zero. That's interference. That's why we see stripes. The arrows for went through left slit and went through right slit sometimes point together, sometimes point opposite, depending on where on the screen you're looking. But when you detect which slit the electron went through, you're not adding arrows anymore. Now you know it went through one specific slit, so you calculate the probability for that slit alone. No arrows pointing opposite, no cancellation, no interference. The math is actually simple. What's hard is accepting what the math means. But what are these arrows really? What do they represent? Nothing. They don't represent anything physical. You can't go find an arrow attached to an electron. It's just a calculation tool, a recipe for getting the right answer. We call them probability amplitudes. Fancy name, but really just arrows. And here's the strange part. The arrows involve imaginary numbers, square root of -1, numbers that don't exist on any ruler. Yet when we square them to get probabilities, we always get regular positive numbers, real things, things we can measure. So reality is built on something we cannot directly see, using numbers that cannot directly exist to predict outcomes that are merely probable. Welcome to quantum mechanics. Now you might wonder, why does nature work this way? What's the deeper explanation? There isn't one. Nobody knows why nature uses probability amplitudes. Nobody knows why the arrows work. We know that they do. Every experiment we've ever done confirms it. But the mechanism behind it, the reason, we have no idea. And honestly, that's okay. Science doesn't always answer why. Sometimes it just answers how. And if you keep pushing, why this, why that, eventually you reach bedrock, the place where the only honest answer is, that's just how nature is. Take it or leave it. So, let me give you an example. Let's go back to something simpler than electrons. Let's talk about light hitting a piece of glass. You shine light at glass. Some reflects, some goes through. About 4% reflects from the front surface, 96 goes through. Simple question. Which photons reflect and which go through? Answer, nobody knows. Can't be predicted. Each photon has a 4% chance of reflecting, 96% chance of going through. That's all we can say. Now add a second surface, the back of the glass. Now photons can bounce off the front or the back. You'd expect about 8% total reflection. 4 from the front, 4 from the back. No. It depends on how thick the glass is. Some thicknesses give you 16% reflection. Some give you 0. 0. The back surface somehow turns off the reflection from the front surface. How do we calculate this? Arrows. We draw one arrow for reflects off front surface. We draw another arrow for reflects off back surface. But here's the key. The direction each arrow points depends on how far the photon traveled. Imagine a little clock that spins as the photon moves, very fast, thousands of rotations per inch for visible light. When the photon reaches a surface, wherever the clock hand is pointing, that's the direction of the arrow. For the front surface, the clock points one direction. For the back surface, the photon traveled a bit farther, so the clock points a different direction. Now we add the arrows. If they point the same way, big arrow, lots of reflection. If they point opposite, they cancel. No reflection. The thickness of the glass determines how much the clock rotates between the front and back surface. So the thickness determines whether the arrows add or cancel.
All right. So we've seen that nature is strange. Electrons behave in ways that make no sense to our everyday intuition. But now I want to show you something even more fundamental. Something that explains why you're sitting in a chair right now instead of falling through it. The uncertainty principle. You've probably heard this phrase before. Most people think it means our instruments aren't good enough. That if we just built better equipment, we could measure things more precisely. No, that's completely wrong. The uncertainty principle is not about bad instruments. It's about nature itself. It's a fundamental limit built into reality. Here's what it says. You cannot know both the position of a particle and its momentum at the same time. Not because you're clumsy, not because your measuring device is cheap, but because the particle doesn't have both a definite position and a definite momentum at the same time. Let me make this concrete. Suppose you want to know exactly where an electron is. You confine it to a very small region. You trap it in a tiny box. Now you know its position very well. But here's the cost. The momentum becomes uncertain. The electron starts moving faster. It has to. The more precisely you pin down where it is, the more wildly its momentum fluctuates. And it works the other way, too. If you know the momentum very precisely, you know exactly how fast the electron is moving, then its position becomes fuzzy. It could be anywhere. The product of these two uncertainties can never be smaller than a certain number, a very small number, Planck's constant. But it's not zero. There's always some uncertainty left over. So, why does this happen? Remember the arrows? Remember how we said particles behave like waves in some sense? Here's the connection. Think about a wave, a perfect wave that goes on forever, same height, same rhythm, repeating to infinity. That wave has a very definite wavelength. You can measure it precisely. But where is the wave? It's everywhere. It goes on forever. There's no specific location. Now think about a short burst, a pulse, just one little bump, and then nothing. Where is it? Easy. It's right there in that small region. You know its position, but what's its wavelength? Hard to say. It's not really repeating. You can't measure a wavelength from a single bump. It doesn't have a definite wavelength. See the trade-off? A wave that's spread out everywhere has a definite wavelength, but no definite position. A wave that's concentrated in one spot has a definite position, but no definite wavelength. And in quantum mechanics, wavelength is connected to momentum. They're related. Short wavelength means high momentum. Long wavelength means low momentum. So this trade-off between position and wavelength becomes a trade-off between position and momentum. It's not mysterious, it's just how waves work. Any engineer who deals with sound waves or radio signals knows this. If you want a precise frequency, you need a long signal. If your signal is short, the frequency is fuzzy. Quantum mechanics just tells us that particles have this wave nature, and waves have this built-in trade-off. But here's where it gets really interesting. This explains why atoms exist. Think about it. An atom is a nucleus, positive charge, with electrons around it. Opposite charges attract. So why doesn't the electron just fall into the nucleus? Why doesn't it spiral down and crash? Classical physics has no answer. In classical physics, the electron should radiate energy as it orbits, lose speed, spiral inward, and collapse onto the nucleus in a tiny fraction of a second. Every atom should collapse. Matter shouldn't exist. But matter does exist. You exist. The chair you're sitting on exists. Why? The uncertainty principle.
If the electron fell into the nucleus, we would know exactly where it is, right there at the center, position very precise. But then its momentum becomes very uncertain. The electron would be moving incredibly fast, flying off in random directions. It would have enormous kinetic energy.
So the electron can't stay at the nucleus. It gets pushed out by its own uncertainty. And it can't stay too far away either, because the electrical attraction keeps pulling it back. There's a balance, a compromise. The electron settles into a region that's not too small and not too big. Small enough to feel the attraction of the nucleus, big enough to keep the momentum under control. That region is about 1/10 of a billionth of a meter, and that's the size of an atom. Let me say that again. The size of atoms, the fundamental scale of chemistry, biology, everything around you, comes from the uncertainty principle. Without quantum mechanics, there are no atoms. Without atoms, there are no molecules. Without molecules, there's no chemistry. Without chemistry, there's no life. You exist because the uncertainty principle won't let electrons collapse into nuclei. And there's more. This is why you don't fall through the floor. When you stand on the ground, the atoms in your shoes get close to the atoms in the floor. If you try to push them closer together, squeeze them into a smaller space, the electrons resist. Their positions would become more certain, which means their momenta would become more uncertain. They'd start moving faster. They'd push back. That's what solid means. That's what hard means. The resistance of matter to being compressed is a quantum mechanical effect. In classical physics, the best arrangement of positive and negative charges would be all of them sitting on top of each other. Everything collapsed to a point, but quantum mechanics says no. You can't confine particles to a small space without paying the price in momentum. So the next time you sit in a chair and it holds you up, that's quantum mechanics. That's the uncertainty principle, doing its job, keeping you from falling through to the center of the earth. Now here's something else that classical physics got completely wrong. Energy. In the everyday world, energy seems continuous. You can have any amount you want. You push a car a little, it goes a little. Push harder, it goes more. Smooth, gradual, any value is possible. But in the atomic world, energy comes in steps, specific amounts, like a staircase, not a ramp. Think of it this way. Imagine you're climbing a hill. In classical physics, you can stop at any height, halfway up, a third of the way, any fraction you like. But atoms are different. Atoms are like a building with floors. You can be on the first floor, the second floor, the third floor, but you cannot stand between floors. Those in-between positions simply don't exist. An electron in an atom can have certain energies, specific values, not anything in between. Why? Because the electron is confined. It's trapped in the space around the nucleus, and confined waves can only vibrate in certain ways. Think of a guitar string. It's fixed at both ends. When you pluck it, it vibrates, but it can't vibrate any way it wants. It has a fundamental frequency, the lowest note. Then it has harmonics, higher notes at specific frequencies. You don't get a continuous range, you get specific notes. Same with electrons in atoms. The electron wave has to fit around the nucleus in a certain way. Only certain patterns work, and each pattern has a specific energy. We call these energy levels, and this explains something beautiful. Light. When an atom is in a high energy level, it can drop to a lower one, but it has to lose that energy somehow. Where does it go? It comes out as light, a photon. And here's the key. The photon carries exactly the energy difference between the two levels. Not approximately, exactly. Since the energy levels are specific, the energy of the photon is specific. And the energy of a photon determines its color. Blue light carries more energy than red light. So each type of atom produces specific colors of light, definite frequencies, sharp lines. Hydrogen produces certain colors. Helium produces different colors. Sodium produces that yellow-orange glow you see in some street lamps. So, if you look at the light from a distant star through a prism, spreading it into a rainbow, you see dark lines, specific colors missing. Those are the fingerprints of atoms. Each element absorbs and emits specific frequencies. By reading those lines, we can tell what stars are made of billions of miles away, all because energy in atoms comes in steps, not smooth gradients. And here's something that puzzled people for decades. Why those specific steps? Why those particular energy levels? Now you know. The uncertainty principle, the wave nature of particles. Confined waves can only have certain patterns. Those patterns determine the allowed energies. Everything connects.
Now, let me tell you about something even stranger. The quantum world has rules that seem completely arbitrary, ridiculous even. For example, electrons refuse to be in the same state. What does that mean? If you have an atom with many electrons, they don't all crowd into the lowest energy level. That would be the most economical arrangement, right? Everyone on the ground floor? But no. Only 2 electrons can occupy each level, and those 2 have to be spinning in opposite directions. After that, the level is full. The next electron has to go to a higher floor. This is called the Pauli exclusion principle, and nobody knows why it's true. It just is. But without it, chemistry wouldn't exist. Think about it. If all electrons could pile into the lowest level, every atom would behave the same way. Carbon would be like oxygen, would be like iron. All the electrons huddled at the bottom. No variety. But because electrons have to spread out into different levels, different atoms have different arrangements. Different arrangements mean different chemical behaviors. Carbon acts like carbon. Oxygen acts like oxygen. Iron acts like iron. The periodic table, all of chemistry, exists because electrons refuse to share the same state. And this same principle explains why matter has volume, why atoms take up space, why you can't squeeze things indefinitely. The electrons in the outer parts of atoms cannot fall inward because those inner levels are already occupied, full, no vacancy. So matter is rigid. Tables are solid. You don't fall through floors. It's strange, isn't it? The rules seem arbitrary. Why 2 electrons per level? Why not 3? Why not 10? I don't know. Nobody knows. These are the rules nature plays by. We discovered them by doing experiments, by looking carefully at how atoms actually behave. The rules work. They give predictions that match reality to incredible precision. But the deep reason behind them? Still a mystery. And maybe there is no reason. Maybe asking why at this level is like asking why the rules of chess are what they are. They just are. You learn them. You play the game. Nature has rules. Our job is to discover them, whether they make sense to us or not. So where does all this leave us? We started with a simple experiment, electrons going through 2 slits, and we ended up having to throw away almost everything we thought we knew about reality. Particles don't have definite positions until you look. They don't take definite paths. They exist as clouds of probability, described by arrows that we add together. The act of observation changes the outcome, and there are fundamental limits to what can be known, not because we're ignorant, but because nature itself is fuzzy at the bottom. This bothers people. It bothered a lot of very smart physicists. Some of them spent their whole lives trying to find a way around it, trying to prove that underneath all this uncertainty, there must be some hidden machinery, some deeper layer where things make sense again, where particles have real positions and real paths that we just can't see. So far, every attempt has failed. Every experiment we've done confirms the quantum picture. The fuzziness is real. The probabilities are fundamental. There's no hidden clockwork underneath. Now, you might ask, if particles don't have definite properties until we measure them, what's really going on? What is reality, actually? Honest answer? We don't know. And here's something that might bother you even more. The theory doesn't tell us. Quantum mechanics is a set of rules for calculating probabilities. It tells you what you'll observe when you do an experiment. It doesn't tell you what's happening when you're not looking. Some people say the particle is in many states at once until you observe it. Some say there are many parallel worlds where every possibility happens. Some say the question itself is meaningless. We should only talk about what we can measure. These are interpretations, philosophy. They all give the same predictions. There's no experiment that distinguishes between them. So physicists mostly shrug and say, use whatever picture helps you think, as long as you get the calculations right. But let me tell you what we do know for sure. The theory works. Quantum electrodynamics, the theory of how light and electrons interact, has been tested to extraordinary precision. We can calculate certain quantities to 10 decimal places, and the experiments match. 10 decimal places. That's like measuring the distance from one city to another and getting it right to the width of a hair. No other theory in the history of science has been tested this precisely, and quantum mechanics passes every test. So whatever is going on underneath, whatever reality really is, the rules we've discovered are correct. They work, they predict, they explain. And look what they explain. Why atoms exist, why matter is solid, why different elements have different properties, why the sun shines, why chemistry works, why you can read these words with eyes that evolved over millions of years in a universe built on quantum rules. Everything around you, everything you've ever touched, seen, or experienced is made of particles obeying these strange laws. And here's the thing, you don't notice it. Day to day, the world seems perfectly normal. Objects have positions, things take definite paths. Cause leads to effect in sensible ways. Why don't we see the quantum strangeness? Because we're big. We're made of billions and billions of atoms. And when you have that many quantum particles together, the weird effects average out. The interference patterns get so fine that you can't detect them. The uncertainties get so small compared to everyday scales that they disappear. It's like this. Each atom is doing something strange, but they're all doing strange things in different ways. And when you add it all up, it looks smooth, it looks classical, it looks normal. The quantum world is always there, underneath, but it's hidden by sheer numbers. So, what have we learned? We learned that nature is not obligated to make sense to us. Our brains evolved to track fruit and avoid predators, to deal with medium-sized objects moving at medium speeds. We didn't evolve to understand atoms. We didn't evolve to visualize probability amplitudes. And yet, somehow, we figured it out anyway. That's the amazing part. Not that nature is strange, but that we, these collections of atoms, these temporary patterns of matter, managed to discover the rules. We built detectors and did experiments and wrote down equations. And the equations work. We don't know why the rules are what they are. We don't know what's really happening when we're not looking. We don't have a satisfying picture that fits human intuition. But we have something better than intuition. We have a theory that predicts what will happen. And when we do the experiments, it's right. Every time. That's physics. That's quantum mechanics.